Hello, I'm Jason Held on behalf of Saber Astronautics. I'd like to welcome you to the Predictive Interactive Ground Station Interface. It's a product which we believe is going to be the next generation in satellite control. PIGGY, as we affectionately call it, is software. It sits on your satellite ground station, and it allows your operators to really understand what's going on inside the satellite and also how those insides are affected by everything happening outside that satellite. Armed with this information, we believe that it's going to allow you to cut the cost of your mission operations by up to 66%. Now, a bit about us. We're a small group, but we're packing a lot of punch as far as our technical capabilities are concerned. We've got guys who worked on Hubble and the ISS. We've got PhD graduates from the world-class robotics lab at the University of Sydney. And we've got decorated officers from Army and Air Force Space Command. This is the problem. We all talk about reducing the barriers to entry to space, which usually means reducing the cost of launch or the cost of engineering of the satellite. But what a lot of people don't realize is that the cost of your operations actually accounts for up to a third of the cost of your total mission. Right? Looking at this slide, you could see why. There's a lot of contextual information. There's a lot of data. And the more complex the satellite, the more data you get, which means you hire more people. And it's all 2D, so there's no context, which means there's higher costs in labor and satellite downtime and training and insurance. Now, if you could dim the lights, imagine if you would, you are a space operator using PIGGY, and forget about text on a screen. Now you're visualizing everything. It's all right in front of your face. You can move around. You could control the scientific information like magnetic field models like you see here. Or you could click on a satellite in your inventory and take a closer look and view the sun ray casting straight to the satellite in the shadows, so you get real good situational awareness and environmental information. But what you really want to know is what's happening inside that satellite. So there you go. You could expand it out and look inside the guts. You can isolate different subsystems like your structures or your command and data handling, or your electric power subsystem, for example. And the important thing here is that you're in control of all the information you really want to see. It's very easy to find. It's there at a click of a button. But what happens if something goes wrong? Now the system needs to tell you something's going on. So let's say you have a solar flare or some other space weather event, and there you go. Components start turning red. Red means there's a defect that needs to be managed. Blue means that there's a defect that happened that you just need to take a look at, but it's recovered. So the point is the system is now prompting you for the information that's most important for your mission operations. Okay, now on the back end, we have complex systems models which are proprietary, which are world-class artificial intelligence, which can tell you the cause and effects of all your defects as they cascade through your system. This is important. The stuff on the left-hand side you're seeing is an actual event, space weather event, that happened on the NASA ACE Explorer. On the right-hand side, you see a chart which shows you the output from our model. And as you can see, they're almost exactly the same. It's dead-on accurate. Our stuff works, right? So the graph below where you're seeing those circles and lines, what that's showing you is the actual variables and what's affecting what. That's showing you that the space weather and all the downstream effects to your satellite components. That's something we hand to our customers. This AI stuff gives us a unique advantage that we are the first in the world who's able to solve this important problem. And this is something that people have been trying to crack on in the mission operations community for the last 20 years. So what it does is understanding these relationships helps you reduce your risk. And reducing risk is to reduce costs. So there are a wide range of industries that are now paying attention to what we're doing and want to partner and collaborate with us. Areas such as transportation, finance, and energy are just the tip of the iceberg. But we don't want to talk about that. We want to talk about the satellite market, right? It's a $169 billion market. About 20 to 60 billion is in operations. And let's not forget about the $1 billion satellite insurance market. So we segment this into three different groups. Just think of it as large, medium, and small, but it's large, micro, and nano. The large market is kind of special because it's very high dollar value, and it's a fairly stable market, and they're more interested in the diagnostics tools than maybe the graphics at this point, but that's okay because the micro and nano guys, the smaller folk, are more interested in graphics and telemetry services, which for us works out really, really well in our business model because we're looking at an entry to the market by providing telemetry and operations services from Australia. We're there, we've got boots on the ground, we can support this type of a mission. And using that as development, as we develop from R&D up into the product state later on in 2014. So how this translates to revenue is we're looking at being cash flow positive with the first microsat sale at the end of year 2, and years 3, 4, and 5 scale up as we start getting the larger satellites online at about $1.2 million per satellite. So that gives us some possible strategic exits of an acquisition, or if we want to, we can sit around for another couple of years and look at an IPO. So in conclusion, guys, this is a great project. It's a game changer for the operations community. It's going to save them a lot of money, and we're ready to go today. So thank you for your time. What are your questions?
So you're planning on a single station in Australia for LEO?
Yeah, just to start off with, and we have an office. I mean, we are a small company, but we have an office with it's top floor, 3rd story. We got great line of sight.
For how long?
Well, we got it till 2014. Our lease is extendable. I mean,
visibility of particularly with small sats and the other ones because they're moving pretty quick. Right?
Yeah, 15 minutes is pretty normal, right? So the idea is for someone who's developing CubeSats, we see a lot of them here today, right. They got to communicate in this part of the world. So their options are they could talk to the Chinese or the Russians or the Indonesians, or along that track we're in great position. Right. And I'm positioning myself as an ally to these groups here in the United States.
Right. But your service availability is going to be limited by the constellation that's above your base station.
Always.
For a period of time.
Always, yeah.
Yeah, in your plan write-up, you said that you were under discussion with Optus in Australia to try an experiment with them in August for trying your software with them. Question was, is that on track for an August demo, and what exactly are you going to try to do with them?
Well, I can't talk in too many details about that. That's something that I really wanted to keep only on the business plan that you guys saw. But cat's out of the bag. Look, we have plans to take some data that they have that's old and repeat the experiment that we did on the NASA ACE Explorer. Right? So the NASA ACE is Advanced Composition Explorer. It's a space weather satellite, which is really good for us because we're able to make the connections between the space weather that's happening, that it's receiving on its sensors, and the actual effects on the satellite itself, and it worked great. So they're interested in seeing if we could repeat that for one of their satellites, that they know where the defects were, and to see if we could recreate that.
I wanted to delve into the market size estimates a little bit more. We deal a lot with the geosynchronous satellites, and there, depending on the size of your fleet, you're spending $1 million to $2 million per year on flight operations, and maybe 1% on in-orbit insurance. You're talking about $1 million plus per satellite. How have you tested that price point? What sort of interest or pushback are you getting from the commercial satellite industry?
We're not pushing any price point to our potential customers yet. The discussion is, let's see if it works, because there's, especially for what we're proposing, since people have been failing at solving it for so long, there's kind of a, people want to see it work first before we talk price. But the 1.2 million comes from previous discussions I had on the operations side when I was an Army Space Support Team officer, trying to do this from the other side of the coin. The offers that we were getting to do mission operations software without any predictive capability was roughly within this range. So, I understand your point. The customers might have a different pricing point. We're going to explore that as we go on.
So, not being a technical person, there's no way to retrofit satellites, so you can get the status of existing satellites, right?
Here's a simple way to think about it.
So your market is the future satellites that are being launched.
Yeah, here's the thing. Here's the way to think about it very, very simply to understand contextually the technology. right now everybody knows what happens on a satellite. You get telemetry, you get a lot of information. You put it on this 2D screen and it lists, and if it does have automated alerts, if there's something wrong, you're sitting on your cup of coffee and an alarm goes off, you run to the monitor, but it doesn't tell you why. So for example, the Hubble Space Telescope team they'd have their screen like the Matrix looking for a word to turn red, and if something happened, then the whole team would gather together and spend hours, days, in some cases weeks with Excel spreadsheets trying to find correlations for a very complicated dynamic emergent system. And a lot of the times it comes down to intuition, because that's how we as human beings try and mitigate this problem. And what I'm saying is that we've got a system that's able to automate that whole thing for them.
So for instance, in that example with the
Yeah.
Hubble telescope, could you have told them what was wrong?
With this, yes.
Thanks.
Related to that validation test on the ACE data that you mentioned, that spacecraft was launched in '97, so the electronics are probably '95 vintage at best. And my question is during the 16 days you were testing that data against your models and whatnot, did they have any anomalies? And if they had anomalies and your system was plugged in, could they have done anything with that new knowledge of what happened?
Okay, I love this question, actually, because this is kind of cool. We didn't test it over 16 days. We gathered the data over 16 days, about 2 weeks worth to train models, right? And we trained it on the 2003 space weather event, which was one of the biggest events of its time. And we then tested it on data all through the next 5 years. So what that tells you, 8 years. So the 2011 space weather event, the models were still accurate. So what that tells you is that this model was time invariant. So the model that was formed in 2003 was still valid time after time after time up until the very last point. Now, I don't want to oversell it because, I mean, as far as research, there's a lot in here which is still quite new. And there are anomalies and errors here and there that we're finding, and that's just part of the process. But the fact that we were able to successfully do that and that the models are still valid 8 years later is a pretty strong statement. So, thanks.